No matter what you may have heard, make no mistake, physics is not over in any sense of the word. As far as we've come in our attempts to make sense of the world and universe around us, and we have come impressively far, it's absolutely disingenuous to pretend that we've solved and understood the natural world around us in any sort of satisfactory sense. We have two theories that work incredibly well. In all the years we've been testing them, we've never found a single observation or made a single experimental measurement that's conflicted with either Einstein's general relativity or with the Standard Model's predictions from quantum field theory. If you want to know how gravitation works or what its effects on any object in the universe will be, general relativity has yet to let us down. From tabletop experiments to atomic clocks to celestial mechanics to gravitational lensing to the formation of the great cosmic web, its success rate is 100%. Similarly, for any particle physics experiment or interaction conceivable, whether mediated via the strong, weak, or electromagnetic force, the Standard Model's predictions have always been found to agree with the results. In their own realms, general relativity and the Standard Model can each lay claim to be the most successful physics theory of all time. On the one hand, general relativity, our theory of gravity, was a radical concept when it first came out, so radical that it was attacked by many on both philosophical and physical grounds for many decades. How could space and time not be absolute quantities? How could they be different for everyone dependent on the particular properties of whoever's observing it? How could gravitation not be instantaneous between any two objects that would attract? How can this interaction only propagate at a finite speed that was equal to the speed of light? How could gravity not only affect masses, but all forms of energy, including massless objects like light? Conversely, how could all forms of energy, not just mass, affect how all other objects in the universe experience the effects of gravity? And how could there be an underlying, warped and curved geometry to the universe that determined how objects moved? Regardless of how anyone might have felt about the new picture that Einstein's greatest achievement, the general theory of relativity, brought along with it, the behavior of physical phenomena in the universe doesn't lie. Based on a whole suite of experiments and observations, general relativity has proven to be a remarkably successful description of the universe, succeeding under every conceivable condition that we've been able to test, whereas no other alternative does. What general relativity tells us is that the matter and energy in the universe, specifically the energy density, the pressure, the momentum density, and the shear stress present throughout spacetime, determines the amount and type of spacetime curvature that's present in all four dimensions, the three spatial dimensions, as well as the time dimension. As a result of this spacetime curvature, all entities that exist in this spacetime, including, but not limited to, all massive and massless particles, move not necessarily along straight lines, but rather along geodesics, the shortest paths between any 2 points defined by the curved space between them, rather than an, incorrectly, assumed flat space. Where spatial curvature is large, the deviations from straight line paths are large, and the rate at which time passes can dilate significantly as well. Experiments and observations in laboratories, in our solar system, and on galactic and cosmic scales all bear this out in great agreement with general relativity's predictions, lending further support to the theory. Only this picture of the universe, at least so far, works to describe gravitation. Space and time are treated as continuous, not discrete, entities, and this geometric construction is required to serve as the background space-time in which all interactions, including gravitation, take place. On the other hand, there's the Standard Model of particle physics. Originally formulated under the assumptions that neutrinos were massless entities, the Standard Model is based on quantum field theory, where there are fermionic quanta, particles, that have charges, bosonic quanta, also particles, that mediate the forces between particles with the relevant charge, and a quantum vacuum of spacetime through which all of the quanta travel and interact. The electromagnetic force is based on electric charges, and so all 6 of the quarks and the 3 charged leptons, electron, muon, and tau, all experience the electromagnetic force, whereas the massless photon mediates it. The strong nuclear force is based on color charges, and only the 6 quarks possess them. There are 8 massless gluons that mediate the strong force, and no other particles are involved in it. The weak nuclear force, meanwhile, is based on weak hypercharge and weak isospin, and all of the fermions possess at least one of them. The weak interaction is mediated by the W and Z bosons, and the W bosons also possess electric charges, meaning they experience the electromagnetic force and can exchange photons as well. This intricate dance of particles and forces, governed by the principles of quantum mechanics, paints a picture of the universe at the smallest scales. Unlike general relativity, where space and time are treated as continuous entities, the Standard Model treats these interactions in a fundamentally discrete manner. Each particle and force has its role, contributing to the rich tapestry that forms the fabric of our universe. Yet, even with its remarkable successes, the Standard Model has its limitations. It doesn't incorporate gravity, and it doesn't fully explain dark matter, dark energy, or the masses of the neutrinos. There's a rule in quantum physics that all identical quantum states are indistinguishable from one another, and that enables them to mix together. Quark mixing was expected and then confirmed, with the weak interaction determining various parameters of this mixing. Once we learned that neutrinos were massive, not massless as originally expected, we realized that the same type of mixing must occur for neutrinos, also determined by the weak interactions. This set of interactions, the electromagnetic, weak, and strong nuclear forces acting upon the particles that have the relevant and necessary charges, describes everything that one could want to predict particle behavior under any imaginable conditions. And the conditions we've tested them under are extraordinary. From cosmic ray experiments to radioactive decay experiments to solar experiments to high-energy physics experiments involving particle colliders, the Standard Model's predictions have agreed with every single such experiment ever performed. Once the Higgs boson was discovered, it confirmed our picture that the electromagnetic and weak force were once unified at high energies into the electro-weak force, which was the ultimate test of the Standard Model. In all of physics history, there's never been a result the Standard Model couldn't explain. But there's a catch. All of the Standard Model calculations we perform are based on particles that exist in the universe, which means they exist in space-time. The calculations we typically perform are done so under the assumption that space-time is flat, an assumption that we know is technically wrong, but one that's so useful because calculations in curved space-time are so much more difficult than they are in flat space. And such a good approximation to the conditions we find on Earth that we plow ahead and make this approximation anyway. After all, this is one of the great methods we use in physics. We model our system in as simple a fashion as possible in order to capture all of the relevant effects that will determine the outcome of an experiment or measurement. Saying, I'm doing my high-energy physics calculations in flat spacetime rather than in curved spacetime doesn't give you an appreciably different answer except in the most extreme conditions. But extreme conditions do exist in the universe. In the spacetime around a black hole, for example. Under those conditions, we can determine that using a flat spacetime background is simply no good, and we're compelled to take on the Herculean task of performing our quantum field theory calculations in curved space. This is where the quest for quantum gravity comes into play. One of the most promising approaches is string theory. Imagine a universe where the fundamental particles are not point-like dots, but tiny vibrating strings. These strings, vibrating at different frequencies, give rise to the various particles and forces we observe. String theory elegantly unifies all fundamental forces, including gravity, under a single framework. Yet, it remains unproven, as the energy scales required to test it are far beyond our current technological reach. Another contender is loop quantum gravity. This theory suggests that spacetime is not a smooth continuum, but rather composed of discrete, loop-like structures. By quantizing spacetime itself, loop quantum gravity provides a fascinating glimpse into the granular nature of the universe. However, like string theory, it faces significant challenges in experimental verification. Beyond these theoretical frameworks, innovative experiments are being designed to probe the quantum nature of gravity. Scientists are exploring the behavior of particles in extreme conditions, such as those near black holes or in the early universe. Let's consider one of the most inherently quantum experiments ever performed, the double slit experiment. Imagine sending a single quantum particle through the apparatus. If we observe which slit the particle goes through, the outcome is completely determined. The particle behaves as though it was destined for that slit, and we can measure its electric, magnetic, and even gravitational fields throughout its journey. However, what if we don't observe which slit it passes through? The particle's position becomes indeterminate until it reaches the screen. Even after the critical measurement, its past trajectory remains a mystery. Quantum field theory allows us to determine the electric field. But without a quantum theory of gravitation, we cannot ascertain the gravitational field or its effects. In this sense, and especially at scales rich with quantum fluctuations or singularities where classical general relativity fails, we don't fully understand gravitation. Our lack of understanding extends to the quantum vacuum itself. The quantum vacuum, or the properties of empty space, can be measured in various ways. For example, the Casimir effect measures the effect of electromagnetic interactions in empty space by altering the configuration of conductors. The expansion of the universe, when measured throughout cosmic history, reveals the cumulative contributions of all forces to the zero-point energy of space, the quantum vacuum. But can we quantify the quantum contributions of gravitation to the quantum vacuum? Not yet. We don't understand gravity's behavior at high energies, at small scales, near singularities, or when quantum particles exhibit their inherently quantum nature. Similarly, we don't understand how the quantum field that underpins gravity behaves under any circumstances. This is why attempts to understand gravity at a more fundamental level must persist. Even if our current efforts turn out to be wrong, identifying the key problem that needs to be solved to push physics forward is a significant achievement. The only options are to keep trying or give up.